We've talked at length about how to determine an electronic band structure given the chemistry and the crystal structure of a material. In this module, we're going to look at how the electronic band structure can actually determine the physical structure. And in particular, we'll talk about a structural distortion, which is called the Peierls distortion. And we'll start by using our simple prototypical example of a one-dimensional chain of hydrogen atoms that have a single s orbital on each atom and a single electron. So just a quick reminder then of our linear combination of atomic orbitals theory. For this case, let's make our hydrogen atoms all a distance a apart. So our unit cell length is of length a. So our range of k values is from minus pi over a to plus pi over a. And our energy as a function of k is alpha plus 2 beta cosine Ka, where alpha is the integral phi I star h phi I dv. Phi I is one of the s orbitals, and beta is the integral phi I star h phi j over all space, where I and j are nearest neighbors. And so our band structure, we plot then the energy as a function of k, and k ranges between pi over a and minus pi over a. Our energy has a cosine form like this. Centered around alpha. And the bandwidth is 4 beta because the energies range plus or minus 2 beta above alpha. We can also think conceptually about what the arrangement of the bonding and anti-bonding interactions is between the atomic orbitals across this dispersion. And at k is equal to 0, when the phase of all the atoms in the unit cell in one unit cell is identical to that in the next unit cell, so the phase of all the atoms in all the unit cells is the same, then all the interactions are bonding. If k is equal to plus or minus pi over a, the phase of the atomic orbital in one unit cell is exactly opposite to that of its neighbor, and so all of the interactions between the atoms are anti-bonding. So we can understand also just intuitively why k is equal to 0 is the lowest energy and k is equal to plus or minus pi over a at the highest energy states. Okay, so let's extend this discussion now and make the unit cell twice as big, but without changing the physics. So we're leaving our physical problem the same, but we're just changing mathematically how we describe it. So we still have a linear chain of hydrogen atoms with their s orbitals. They're still spaced a distance a apart, but we're going to work in terms of the unit cell, which is of size 2a. So now K has the range minus pi over 2a to plus pi over 2a. And mathematically, if we solve our linear combination of atomic orbitals theory equations, we obtain that the energy is equal to alpha plus or minus 2 beta cosine Ka. And so let's sketch that. Sketch the energy as a function of K. And now our range of K is half of what it was before. K is ranging from minus pi over 2a to pi over 2a. And again, we have a cosine form. And again, we're centered about alpha, and our bandwidth is 4 beta, because the range runs plus or minus 2 beta around alpha. And we have 2 bands because we had 2 atoms per unit cell, and they're within a range, half of that, which we had in the previous case with 1 atom per unit cell. And of course, the 2 band structures are identical. The band structure that we plotted when we had 1 atom per unit cell and this one, because the periodicity now is 2a, and so our wave function psi of k is identical to psi of k plus n pi over a for the doubled unit cell case. And so if we continue and replot our single unit cell case on the same axes, we see that this region of the band structure here in the double unit cell case is exactly the same as this region of the band structure here. When we take k plus 2 pi over a, we get exactly the same value for the energy. And likewise, this region of the band structure here has just been reproduced. It's been folded back into the narrower, smaller region of K space. If we want to look at the intuitive picture of the combinations of atomic orbitals that give rise to this band structure, then we can work in terms of bonding and anti-bonding combinations of the unit cell. So we see that the unit cell now contributes 2 bands. One from its bonding combination, and 1 from its anti-bonding combination. And so if we start within the unit cell with an antibonding combination, or within the unit cell with a bonding combination, we can then work out for different K values what the energy of these combinations is. So let's look at the antibonding combination and the bonding combination, first at K is equal to 0. And so what it means to be at K is equal to 0 is that each unit cell is identical to the first, and so for the antibonding combination, which is antibonding within the unit cell, it's also antibonding between the unit cells, and so this one is the most antibonding possible combination. Likewise, the bonding combination at K is equal to 0 has each unit cell identical to its neighbor, and so it's both bonding within the unit cell and bonding between the unit cells, and so this is the most bonding combination. And so these two combinations correspond to the most bonding and the most antibonding combinations that we see on our band structure here. Now let's look at K is equal to pi over 2a for the antibonding combination within the unit cell first, and K is equal to pi over 2a is the boundary of the Brillouin zone, and so this means that each unit cell has its phase exactly opposite to that of the neighboring unit cell. And so for the antibonding combination within the unit cell, we end up with this arrangement, which we see as antibonding within the unit cell, then bonding between the unit cells. So this is actually a non-bonding orbital, and so its energy is the same as that of an isolated hydrogen atom. Now we do the same for the bonding, the combination that's bonding within the unit cell. We'll reverse the phase between the unit cells. And we see that although it was bonding within the unit cell, it's now antibonding between the unit cells. And so it's non-bonding, and it has the same energy as the orbital that was antibonding within the unit cell at K is equal to pi over 2a. And so we can understand intuitively this degeneracy at pi over 2a. Okay, so that was a review. Now what we're going to do is dimerize the structure so that these states at K is equal to pi over 2a are no longer degenerate. They no longer have the same energy. So instead of having a chain of equally spaced hydrogen atoms, we have a chain of dimerized hydrogen atoms. The unit cell size is still 2a, but the atoms within the unit cell are closer together than the atoms between the unit cells. So now if we look at the bonding combination at K is equal to plus or minus pi over 2a, within the unit cell, the two atoms have the same phase. Between the unit cells, they have opposite phase, and so on. then we still see that it's bonding between the unit cells, and it's anti-bonding. It's bonding within the unit cells, sorry, and anti-bonding between the unit cells. But because the atoms that are bonding are very close together, then the bonding interaction will be very strong, to be very bonding. Whereas because the atoms that are anti-bonding are rather far apart, then the anti-bonding interaction will be not very strong. The combination that was anti-bonding within the unit cell at the zone boundary at plus or minus pi over 2a is anti-bonding within the unit cell, and it's very strongly anti-bonding because these atoms are now close together, whereas between the unit cells it's bonding but not very strongly anti-bonding, not very strongly bonding, because these atoms are now far apart. So these two orbitals no longer have the same energy. The bonding one is now lower energy. The anti-bonding one, the one that's anti-bonding within the unit cell, is now higher energy. And if we sketch our band structure again, energy versus K, between pi over 2a and minus pi over 2a, let me first sketch how it looked before we dimerized. Now that we dimerize, then the states at plus and minus pi over 2a that were previously degenerate are no longer degenerate. And the lower energy one is the one that's bonding within the unit cell, and the higher energy one is the one that's anti-bonding within the unit cell. Mathematically, we could have reached the same result by recognizing that the beta integral for the two atoms within the unit cell, those that are close together, that are dimerized, is not equal, in fact it's greater than the beta for the two atoms between the unit cells, the two that are further apart. The next thing to notice is that for a chain of hydrogen atoms with one s orbital per atom and one electron per atom, we have one electron per atom and one orbital per atom, then our band is half filled, or our manifold is half filled, and our Fermi energy that would have been exactly at this energy level in the dimerized case is now in the gap. So our system that would have been metallic, our one-dimensional chain of hydrogen atoms of 1s orbitals in the LCAO theory with one electron per atom as a metal, but when we take into account, or when we allow it to dimerize, then it becomes an insulator. And we see that these electrons that in the undimerized case were in the region of the band here are now at lower energy in the dimerized case. So the dimerization lowers the electronic energy and so we'd expect it to occur spontaneously because it results in a lower energy system. So we would predict, based on these arguments, that a one-dimensional chain of s orbitals with one electron per atom would spontaneously dimerize to give a lower energy system, and it would be insulating when it did that. Of course, there's a cost to dimerizing, which in terms of the structure, deforming the structure and causing a strain. And so whether a system dimerizes or not, or has such a structural distortion, depends on a balance between the lowering of the electronic energy and the structural strain energy cost. So deforming the structure costs a strain energy, however. And so it turns out, if one carefully takes into account the lowering of the electronic energy in contrast to the cost in strain energy, one finds what's known as the Peierls theorem, which is that a one-dimensional metal such as the linear chain of s orbitals, each containing one electron, is always unstable with respect to a structural distortion So that means it will spontaneously undergo a structural distortion. And the distortion that it makes is one that lifts the degeneracy, takes away the degeneracy between the degenerate orbitals at the Fermi energy. So whenever we have the case of a metallic system that has degenerate energy bands, bands of the same energy at the Fermi level, it's always the case that it will be able to lower its electronic energy by making a structural distortion that will open a gap at the Fermi energy. In some cases, that will cost too much strain energy, but in the case of a one-dimensional system, the lowering in electronic energy will always win. And so it's always the case that it will want to make such a structural distortion, and then it will become an insulator. We can go a little bit further. So here, in our example, the periodicity of the distortion by that I mean the size of the new unit cell, is equal to 2a. And let's write 2a as pi divided by pi over 2a, because we can notice that pi over 2a here is equal to the Fermi wave vector. It's the k value at the Fermi energy. And one can generalize this observation and say the period of what's called the superlattice, the new lattice after the distortion, is half the wavelength of the top filled energy level, the energy level at the Fermi energy. So the periodicity is the Fermi wavelength over 2, or half. Remember, the wavelength is 2 pi over k, 2 pi over the Fermi wave vector, or just pi over the Fermi wave vector. Okay, so let's finish then with an example, a real example. Which is polyacetylene. So this is a polymer that's made by polymerizing ethine, which is also called acetylene, which is C2H2, and it's often drawn like this. So the carbon background or backbone is often drawn as alternating double and single carbon bonds, and each carbon has a hydrogen atom bonded to it. But what we'll see is that these this picture of alternating double and single bonds is not entirely appropriate. So most of the valence electrons, so 3 valence electrons per carbon atom plus 1 per hydrogen atom, are tightly bound in deep covalent bonds. But each carbon has one of its 4 valence electrons left over, which goes into its p orbital that's perpendicular to the plane. So it contributes 1, let's call it a pz orbital, which is perpendicular to the plane of the molecule. So it has 1 pz orbital and 1 electron that are not tied up in these deep, low-lying energetic covalent bonds. And so if we take a look from the side, so looking at the polymer from the side on, then one sees a row of carbon atoms, and each of them has a p orbital that's perpendicular to the chain, and we're interested in the bonding now, the band that's formed by these p orbitals. And so if we do a sketch, simple sketch of the band structure, energy versus K, 0 to plus or minus pi over A, since we assume the carbon atoms are a distance A apart. Then our band structure has the usual cosine form. Centered around the energy of an isolated p orbital and with bandwidth 4 times the beta integral for the pp pi interaction. At k is equal to 0, we have the most bonding combination. All of the p orbitals have the same phase, so they have a bonding pi interaction. And at k is equal to plus or minus pi over A, we have the most anti-bonding interaction. Each adjacent p orbital is out of phase, so we have the most anti-bonding pi interaction. And if we forget about the discussion we just had about the Peierls distortion, each carbon atom donates 1 orbital and 1 electron. And so the band would be half filled, the Fermi energy would be halfway up. And so naively, we would expect a half-filled band. And metallic behavior. If we take into account the Peierls theorem, then we would predict a structural distortion, a dimerization, it would be a dimerization because the Fermi energy is at pi over 2a, so we expect the unit cell to double, and this would open a band gap and give us insulating behavior. And so what happens, in fact, is that polyacetylene is an insulator when it's not doped. The band gap is 2 electron volts, so it's quite a large gap. It's definitely a convincing insulator. And it has an alternation of the carbon-carbon bond lengths of 6 picometers. So adjacent carbon-carbon bond lengths, so one long and one short, and the difference between them is 6 picometers. And so the behavior of polyacetylene is certainly consistent with the prediction of the Peierls theorem. Of course, you could argue, well, can't we just think of it as forming a conventional covalent double bond, then a conventional covalent single bond? And if one looks at typical bond lengths for double and single carbon-carbon bonds, we would expect a much larger bond alternation. So typical double versus single carbon-carbon bonds would give an alternation in the bond lengths of around 21 picometers. So polyacetylene then is a nice example of an almost quasi one-dimensional system that shows the physics of a Peierls distortion.